I have two complex numbers here, z1 and z2, written down in their polar form. And we know that when we multiply complex numbers in their polar form, we multiply the values of r and add the angles. And it's in adding the angles that I can imagine multiplying complex numbers as a rotation. Right, if I think about the first complex number being fixed, right, maybe that is my theta 1, and then I have a value of r1. And I come along, and then I multiply that by another angle. And maybe this angle's smaller, and I have a theta 2, and this has an r2. Then I get this other complex number where I take the two angles and I add them together. And so I'm imagining this smaller rotation here, so maybe a little bit of a turn like this. And since I'm imagining these as being r's that are larger than 1, right, the angles have added together and I get this rotation. And then this length is r1 times r2. But just to think about this as a rotation a little bit more, let's imagine that z1 is 2 times the cosine of 30 degrees plus I sine of 30 degrees. And that z2 has an r value of 1 and is the cosine of 350 degrees plus I sine 350. All right, well, I can imagine this situation pretty easily, I think. I have a circle of radius 1 here, and I have a circle of radius 2. My first complex number, the cosine of 30 degrees is, 2 times cosine 30 plus I sine 30 is this angle. And then z2 down here, just a radius of 1, but at 350 degrees, so real close, just 10 degrees away from a full revolution. When I multiply those together, well, this r value is 1, so this one's r is not going to change, but I'm going to add 350 to that 30 degrees, so that's a rotation of 350 degrees, which would put me at 380. So just right here, 20 degrees above, right? I start here, and I add that 50 degrees, and I get right to there. Right, so literally when I multiply these together now, I see z1 times z2 can be thought of as a rotation. And here, the r value is not changing from the first one because I made the second one be 1. All right, and in polar form, of course, I should write that down as an angle that is between 0 and 360 degrees, so I find the coterminal angle 20 degrees. All right, so I've really just rotated the first one because I made the second one have a r value of 1. All right, well, there's one complex number I really like to think about in terms of multiplying a complex number being a rotation, and that's I. If I think about the complex number I, it's 1 unit above the origin at an angle of 90 degrees. So it's cosine of pi halves plus I sine of pi halves. And if you prefer to write 90 degrees there, you certainly can. You can do all of this in degrees. But this means multiplying by I is a rotation of pi over 2 of 90 degrees. Every time I multiply a complex number by I just have turned that original complex number by 90 degrees. And we can see this in powers of I. Maybe a long time ago, someone showed you that because of these two relationships, right? I is the square root of minus 1, I squared is minus 1, and I can establish all of these relationships because of that, right? Just think about I squared being minus 1, multiply both sides by I, and I get I cubed is minus I. I to the fourth is in 1, right? Because I get I to the fourth when I multiply this time by I, and minus I times 1I would be minus I squared, which would be 1. And then we'd watch these values just repeat as we go down, right? Just imagine multiplying both sides by I. But now I could imagine starting at I And then thinking, well, what's I times I? Well, it should be a rotation of 90 degrees, which would leave me right here, and that's the real number minus 1. Multiply by another I, and that's another 90-degree turn, which would put me down here at the complex number minus I. Another 90-degree turn, I to the 4th has to be 1. So here I have I squared, I to the 3rd, and I to the 4th. And as I keep going around, I have I to the 5th, 6th, 7th, 8th. Because multiplying by I is just a 90-degree turn. And so that's another way to think about the fact that this list repeats.